I'm sorry to interrupt. We cannot hear the speaker online.
Okay, yeah. Now you can hear me? Okay.
Yes, much better. Thank you.
Okay, sorry. Yes. Do you also need to, I mean, no, I guess you know the things. Do you want to see the blackboard above, which I talked about before?
No, it's fine. Thank you.
Good. Okay. So, and this is true for every g in G. So we indeed really see, okay, it's a constant function. whatever G I take, it will just be the value what it is at that entity. And very similar just for the other direction. So for the other direction, I mean, what do we want to do? We want to say nu is G invariant and we know it's constant. So we can write the integral of f of x d nu as p nu of f at that identity. And we know it's constant, so we can rewrite this as p nu of f at g, which is the integral of f of gx d nu. And this then means that g nu is equal to nu, because it's true for every function there at low infinity. Okay, so it's really basic proof. Okay, now a nice definition. Namely, we say that a group G is called Choquettini if the following holds, namely, for every mu which is generating we have that the Poisson boundary of G and mu is just a one-point space. Okay? We have yesterday seen an example of a group which is Choquettini. Does someone remember? So Choquettini means that whenever I take any probability measure which really sees the group, I will get trivial Poisson boundary. Yes, exactly. So in fact, we have seen yesterday that all abelian groups are Choquettini. Let me just abbreviate with this with CD. Choquettini. Okay, good. And there is a nice result. Maybe it deserves a new black, whatever. A nice result in Amos of Joshua Frisch, and let me just of Frisch, Hartmann. Maybe I need a new blackboard. Sorry. Omar Tammuz, Vahidi Ferdowski. At least on archive, it was in 2028. I don't know when exactly the Anna's paper appeared. And so, I mean, we have seen here, okay, abelian groups are Choquettini, but are there more groups which are Choquettini? What other groups which are Choquettini? The result is that, so if I first stated for a simpler case, so if we have that G is finitely generated, then we have the following. Namely, then we have that G is Choquettini if and only if G is virtually nilpotent. My V's and my R's are not so easy to distinguish. Meaning that I have a finite index subgroup and this is nilpotent. But more general, we can just have if G is just any countable group. Then we have G is Choquettini if and only if there are no ICC quotients. Meaning that there is no, let's see, Q such that it has the so-called infinite conjugacy class. This is ICC. Infinite conjugacy class property, meaning that for every element Q in Q, which is not the identity, I have that if I conjugate it with elements in G, I get everything. So let with Q, sorry, Q tilde, Q tilde inverse over all Q tilde in Q, and this is infinite. Okay, so I have no ICC quotients, meaning that I can't find such a Q such this holds. Okay. So maybe it's one thing I should say. So this direction here, this was already done by Jaworski in 2004 and in 2007 by Raya. And moreover, so if we are in the case that there is some ICT quotient, so I can find a non-trivial Poisson boundary, then the measure which generates my non-trivial Poisson boundary can be chosen in a nice way. So I can take actually a symmetric measure, and I have finite entropy of this measure. So somehow, if I can find a non-trivial Poisson boundary, the measure I need to do this is actually quite nice. Okay, so why do I highlight this? This is one thing. So on the right-hand side, I have something which really has to do with probability theory. I'm talking about Poisson boundary. And sorry, on the left-hand side. And here on the right-hand side, I have purely algebraic property. So this is already something nice. Let me try to convince you even more. Namely, let me characterize amenability. Is there a question? Yeah. If there exists no ICC quotient. I mean, and this is just the explanation of what ICC quotient means. So this is really just the explanation. And I know G is Choquet-Ligny if G has no ICC quotient. If and only if. Yes, so that's the sentence. Maybe it's not very grammatically correct, I don't know. But so is it clear from the notation here of this? Yeah. Okay, so there exists no ICC quotient if and only if G is Choquet-Ligny. Okay, another nice result, which is due to Rosenblatt in the 1991 and independently by Kamenowicz and Berschik in 83. So they characterized amenability, so G is amenable if and only if there exists some nice measure mu which is generating and spread out. So it's a Borel probability on G such that the Poisson boundary is trivial. Okay, and again, also here, in this case, if we have the G is amenable, actually this measure here can be chosen nicely in a sense that I can actually require that really the support of mu generates my G, not only the semigroup generated, and it's symmetric and stuff. Okay, so this if you want to be fancy, you can add this to your list of characterizations of amenability. Okay. Maybe just because amenability is also an interesting topic now in the discourse, so let us prove the easy direction here. But just really, so this one. So we say we take some mu, which is generating, and we have that the Poisson boundary is trivial. Now, we want to take this characterization of amenability by whenever my group acts on a compact space, then there should be an invariant probability measure. So we say let G act here on some X, which is compact. And we want to show that there exists an invariant probability measure. How can we do it? A priori, we don't know that there exists some invariant probability measure, but what kind of measure do we know that there exists? Exactly. So we have seen that definitely we know that there exists some new improb of X, which is mu stationary. But now, so if this mu is not G invariant, then I know by here, if this is not G invariant, I know that there exists some F such that my Poisson transform is not constant. So I know that there exists some F such that the Poisson transform of mu of F is not constant. Well, but I mean, I do know, the Poisson transform, again, just to remind you, is from L infinity of X nu, sorry, sorry. So say F, so there exists some F in the Poisson boundary of G nu, such that this is not constant. In F, sorry. In L infinity of the Poisson boundary. Okay, but is it possible that I have a function, an L infinity function, on a space which is not constant, but the space is not just one point? I mean, the thing is like, if in order to have a function which is not constant, I need to at least have two values. So I need to at least have 2 points in my space where I can evaluate this function. Otherwise, there is no possibility. So this means that the Poisson boundary of G and mu, basically the size of this would be more than just one. And this is a contradiction. So this means then that really mu has to be G invariant. And this is what we wanted to show. Okay. Good. Are there questions? Yes. Mm-hmm. So you that's a good question. So you mean kind of this you could also characterize in terms of the so-called Fürstenberg boundary, which is basically a topological version of this. So there is no probability measure there, but it's a nice, nice. It's a non-metrizable, but maybe still nice space. Okay. So you asked kind of what, I mean, one of the big advantages of the Poisson to work with Poisson boundaries in general is that you do have a nice compact metric space. It's basically just forgetting about the null set, and then you do have a nice space. So it's sometimes easier to work with the Poisson boundary than it is to work with the Fürstenberg boundary. But you're right. I mean, this for the characterizations itself, you can also do it in these terms. Mm-hmm. No, I think the question does make actually quite a lot of sense, and I do. I mean, I would say yes. It should be possible to go directly there, but I don't know. Maybe I guess I would have to think about it more. But no, it's a good question. So about to kind of go directly from the measure theoretical to the topological boundary, or the other way. Mm, yeah. Does someone in the audience know? Okay, but I mean, I, I would be surprised if not, but people can be surprised. So yeah, okay. Okay. So now I would actually like to go to the second kind of topic uh, of this list, which I gave you in the beginning of what I want to cover. And I want to talk a little bit about so-called commensurated subgroups. And maybe first as a motivation, is that, well, we have already seen that if I have a normal subgroup, then the Poisson boundary of G and mu has as a factor the Poisson boundary of G mod n and the projected measure. And there is also a nice result of Kamanovich, 2002, which says that, well, again, we have n in G being a closed normal subgroup, and we have n is amenable if and only if. So there are two characterizations. One is just there exists some probability measure on G, of course generating, and so on, such that the Poisson boundary of G and mu is isomorphic to the Poisson boundary of its quotient. So what does it mean? It means that if I have an amenable subgroup, I mean, we have already seen amenable groups don't add much to, or at least there is a random walk such that my Poisson boundary doesn't really see this amenable group. And here it means that, well, if I'm quotient out by an amenable group, I don't change much, at least for some probability measure, I don't change much, okay? And equivalently, we can also say for every probability measure here on the quotient, G mod n, we have, there exists some probability measure on the group, So some kind of extension such that, again, the Poisson boundaries are trivial, isomorphic. Okay. So now we can ask, okay, I mean, talking about normal subgroups is kind of quite restrictive. What if we try to somehow weaken this assumption a little bit? There is a concept called almost normality. Okay, so for now on, I want to have really, so I will now I will now talk about discrete groups, and then later I will talk about dense embedding of this discrete group in some totally disconnected locally compact groups, meaning that just for the notation, I need to now say, okay, let gamma now be a discrete group, discrete countable. And I say that a subgroup of gamma is so-called commensurated. There are many names. People also say it's a Hecke subgroup. Or you can also say it's an almost normal subgroup. Depends a little bit in which area you're working, what kind of terminology you want to take. Well, the condition is the following, namely, we call it commensurated if the orbits of this subgroup on any element in the coset space are finite. Okay, so again, what do I mean by this? I mean, this is just a collection of all lambda acting on gamma lambda, where I'm running over all lambda in lambda. Okay. Why are normal subgroups? Why do normal subgroups fulfill this condition? If I have a normal subgroup in gamma, this is commensurated. Since, well, I claim that the orbit of lambda of any n, sorry, of any, sorry, n of any gamma n is just which number? Which size? Yes, exactly. It's just one. Why is it? Yes, yes, absolutely correct. Exactly. Yes, it's I mean, what you said, absolutely perfect, very advanced. But let's do it slowly. So what do we have? We have some n times gamma lambda. What would it be? It would be, well, I know it's normal, lambda, and this is n and then gamma inverse. This would mean then, well, this is n and gamma inverse, and then I can rewrite it again like this. So whatever n here I take in my orbit, I won't see more than one element. Okay, and now I'm doing something super mean because I tell you, yeah, it's a generalization of normal subgroup, and think of normal subgroups, and now I will forbid normal subgroups. And that's the following definition. Namely, we say gamma and lambda, where lambda is a nice commensurated subgroup, is a reduced Hecke pair. If we have the following, namely, if we take the intersection of all conjugates, then we just see one element. So in particular, lambda is not allowed to be normal in gamma. We will see just in a few moments why this is an interesting condition and why it makes sense in our setup then and what it can empower us to do. But just let me put it here. Okay. But other questions so far, then otherwise I would go to an example. So example where we are kind of familiar with again is lamplighter. So again, we take now gamma is just our last lamplighter group. So it's the direct sum over n over c of c modulo 2c semi-direct product c. And yeah, I'm sorry for writing it the other way around, and people are used to it. I don't know. Good. What could be a nice commensurated subgroup here? Or a nice Hecke subgroup here? So there are actually quite many, but one possibility to go would be, well, I don't want to have lambs all over, but I want to have lambs, let's say, only on the positive side. So if I take lambs only on the positive side, from 0 until infinity of c modulo 2c, and I want to have that the lamplighter stands at 0. Why do I want to have the lamplighter stand with 0? If I don't have this, then actually I can just shift this configuration by multiplying group elements and then get everything. So this is, I don't want to shift this. I really want this to be a group. And this is a commensurated subgroup, and we will see in a moment why. Yeah, just let's just do an example and just calculate why it is commensurated in an example. One can do it also more general, but so for instance, if we take the element where I have zeros everywhere, this was this notation where I have only zeros, and I take 1 and I look at lambda. So this is just an element now in my just an element in my coset space, and later I look at the orbit of it. So this is my gamma lambda. Well, what does it do? How was the action? The action was I take this configuration and I add it to this configuration, but before I shift this configuration over here by whatever position I have here. So in this case, it would mean I take this configuration, which starts at 0, and I shift it by 1. And then I add the configuration, which has only 0, so I don't do anything. So what does it mean? It means that I start now at 1, and then I'm at infinity of c modulo 2c, and semi-direct product now I have here 1. Which is okay now, it's not a group, it's okay. Okay, now I want to look at the lambda orbit of this thing. So what is the lambda orbit? Well, I want to take an element now in lambda. So lambda times this O1 lambda. So let's say this is some an sequence where n now goes from 0 until infinity. And I have the position of the lambda at 0. And then I'm acting on what is written here, which we have already calculated. So it's just configuration from 1 until infinity of c modulo 2c semi-direct product 1. So what do I do now? I have now this configuration. I shift this configuration by nothing, and I add these two configurations. So what does it mean? It means here, since I'm allowing every state, whatever is here, it's no restriction. I can basically, it's kind of cancelled out in a sense, like it's absorbed by being allowed to be everything. So what do I get here? I only get that A0 is the only element which is not cancelled out, kind of, which is not absorbed by the whole mass here. So I have A0 plus, and then I have the rest from 1 until infinity of C modulo 2C, semi-direct product 1. Now this would be, the brackets would be here. So this is what I have here. This is my kind of my group. What does it mean for the orbit now? What is now the orbit of lambda of this element, this 0 and then 1 of lambda? What is the size of the orbit? How many elements can I have in this orbit? Exactly. I can have only 2 elements because basically the only way how I get distinguished elements is to change this A0. And this can have only 2 different possibilities. So this A0 here is either 0 or it is 1 because it's in C modulo 2C. So I have only 2 possibilities. That's it. So my orbit is really just 2. Okay? So this is a simple thing. Well, if you take here some higher number, you will have more freedom, but you will still have a finite number. So all your orbits are finite. Okay. And one can also show that it's reduced. Maybe let me just not do it because it would take too much time, but it's not difficult. So if I take overall gamma and I have here gamma, yeah, I don't want to do it. It's an exercise. It's not difficult, it's just writing down these things. Basically, it means that I'm shifting and then I take the intersection of all things which are shifted in any way, which means the only thing which can survive is the identity. Okay. Good. Then why are we doing all this? So what I actually want to do, let me go there. So it would be, no, let me go here because I want to add in later stuff with the example, so it would be good to have it together. So, yeah, sorry, it's a change. Why is it an interesting thing? So there's a concept called shifting completion. Which now some people in totally disconnected groups will love. What do you mean? Yeah? Okay. Yeah. So the question is basically how you want to lift it. There is not a canonical really good way. I know that, for instance, Sarah Proferio, she has done something where she is lifting the thing, but it's not really the way of lifting such that it would be generating. It's a way of lifting of just seeing it as a probability measure upstairs there. And then she is relating the Poisson boundaries of this. But I don't think that there is a canonical way of lifting the whole thing. That's the thing. It's also not canonical, but what we do here is we consider basically gamma mod, not n, but this lambda, take a probability measure here, and then there is also a nice but not canonical way of lifting it to gamma. So it's not about n and lifting it up there, but it's about the quotient and lifting it up to there. Yeah. Okay. So if we have given now gamma and lambda being a nice reduced Hecke pair, then what we know is that there exists some nice okay, let me write it like this. There exists some nice embedding into a totally disconnected locally compact group, such that with respect to the topology on this group, this is dense. And also this commensurated subgroup can be densely embedded into K. K is a subgroup here of G, and this is compact and open. And this is in such a way such that the coset spaces gamma mod lambda are isomorphic of G mod K. And exactly this kind of that at the coset spaces we can pass to the other group is what we use in order to relate the Poisson boundary of gamma and the Poisson boundary of this G, of this totally disconnected locally compact group. There is also another way of not going in this direction, but going in the reverse direction. Namely, if I'm just take some TDLC group, maybe you don't like discrete group, just take a TDLC group. You know there exists a compact open subgroup just by von Mansing. And you have just, if you have this discrete group sitting densely there, just take the pre-image of this embedding and you will get a commensurated subgroup here. So if you don't want to do it in this way, you can also do it in the reverse order. Just take some dense embedding in a TTLC group, take a compact open subgroup, and then you find your commensurated subgroup. Okay. Good. Let's maybe. Okay. How much time? Okay. Do you want to? It's not difficult, but do you want to see how this construction is done, or the Schlichting conflation? You can also look it up. Yes. Okay. Perfect. That's a good compromise. So in the example, so basically what I want to do is I want to somehow complete this thing with respect to, or maybe I just say in words, so you can't just look at gamma as, okay, maybe I just say it. So you can't think of an element in gamma, you can just think of it, well, it's left multiplication, which means that basically you can view gamma as actually sitting inside the permutations of gamma mod lambda. Which means, and here you can also, I mean, you can view it as the maps, and then you have just really gamma mod lambda to its power. And just have the product topology, and now you take the closure of gamma in this product topology. This is how you get G. So then really, G is just the closure of gamma in this topology, in the, let's say in the maps of gamma mod lambda. And the same for K. So in this example, what do we have? So we want to have that we take a commensurated subgroup which allows, which is supported on the positive side, meaning that our G should be that Again, on the negative side, you don't change anything. Let's say, I mean, you can also write 0, it doesn't matter, but just for kind of, yeah. But here, on the positive side, so I always write this plus, meaning only finitely many entries are non-zero. And now I need to allow infinitely many entries to be non-zero from 0 until infinity. And again, just here I don't do anything. And k in this setup would then just be from 0 until infinity, c modulo 2c, semi-direct product 0. Okay, this would be the Schließung completion of this commensurated subgroup. And here you already see something which we have seen in the last lecture, namely there is something looks like a little bit like a Poisson boundary with drift. And this is what we will see later. Basically, this whole method is a way of kind of writing the Poisson boundary as a homogeneous space, which usually you can't do for discrete groups, but we pass through some nice locally compact groups, and there we can write it as a homogeneous space. But before doing all this, I have to tell you, I mean, you can't do it, you can't do it just for any random walk, but you have to choose the random walk such that things work out. Namely, we want to have the random walk such that this behaves nicely, meaning I erase this blackboard. So how to go from, let's say, random walk on gamma to random walk on G and back and forth? Well, we can only do this for a certain class of probability measures. Namely, we call a probability measure on gamma, we call it lambda absorbing, if the following happens. Namely, it should be lambda invariant whenever I take an element in a coset space. It will get clear a little bit later why this is the right notion. So, in particular, it's not a very, I don't know, it's something which actually you can force a measure to do quite. Like you can construct measures which do this quite easily. Namely, just take the whole orbit, the whole lambda orbit of some coset element. Take what mu is giving to this whole lambda orbit, and then spread it equally. So this mass you take and you spread it equally. Every of these elements in the lambda orbit should just get the same value. And this is fine. So it's like if you have a probability measure, to make it lambda absorbing is not such a big deal. And for this thing, we do have the following proposition, which is joint work with Michael Björklund. Hartmut, which means, which says that there exists a nice map from the probabilities measures on gamma, which are lambda absorbing and generating, to the probability measures on G, which are bi-key invariant and generating. And this map is actually surjective. So again, if you don't like lambda absorbing probability measures, start off with any bi-k invariant probability measure here. So bi-k means it doesn't matter if I have on the left-hand side or if I take an element on the right-hand side in k, my probability measure doesn't change. And So whenever you have something like this, you can find a corresponding lambda absorbing measure such that things are nice. Let me write mu is going to rho mu as this kind of map. And this is such that if I restrict this map to gamma mod lambda, this is basically the same as this rho map restricted to G mod K. This is the nice thing how we can pass them here for Poisson boundaries. I could write down explicitly how this rho map looks like, but I'm not sure if people. It's not a big thing, but yeah, if people are interested in an explicit formula, you can ask them after the talk or in the break or whatever. Okay. Because yeah, time is yeah, okay. Time is running. Do you want to see the explicit formula? Is it important to you? Okay. So what we can do with this now is to relate the Poisson boundaries. So this is joint work with the same authors. So if we have, so let gamma and lambda be a reduced Hecke pair, and G and K, it's Schlichting completion. And we have some mu in prop of gamma, which is generating. And lambda absorbing. And we then add let rho mu be as above. Then we have that the Poisson boundary of gamma, Poisson boundary of gamma mu always has as a factor the Poisson boundary of this bigger group with respect to this corresponding measure. And of course, this factor map is just as a gamma factor map. And in fact, we have that this gamma lambda invariant mu boundaries. So all the factors are actually, yeah, just in fact it's lambda invariant. So actually, all okay, let's write like this. So this, yeah, this rho mu boundaries are isomorphic, at least as gamma spaces, to lambda invariant mu boundaries. This is what I want to say. And furthermore, so okay, we know that this is a factor, but you can ask, okay, what happens if they are the same? So if we have that the Poisson boundary of gamma and mu is isomorphic to the Poisson boundary of G and rho mu, then you know that the commensurated subgroup lambda is amenable. The reverse direction is true in the set of unique stationarity. So if you know that your Poisson boundary here there is only one stationary measure on this realization, and you can't find any other stationary measure, then you can also have the reverse direction. So then you know that whenever your commensurated subgroup is amenable, the Poisson boundaries are isomorphic. Okay, and maybe so. Again, this whole theorem, as what I said before, with this, if you don't want to start with some mu generating and lambda absorbing, just start with something by k invariant. You can find something this and all this holds as well. So it's works like this as well. And let us maybe just prove why this is amenable, just because amenability is kind of something you are now familiar with. So just proof of lambda being amenable in this case. So if we have that, so we have that gamma is acting on the Poisson boundary of gamma and mu, and this is always a semi-amenable action. Well, amenability also passes down to subgroup actions, so it means that lambda acting there is also amenable. Well, but I also do know that the Poisson boundary here by assumption is isomorphic to the Poisson boundary of G and rho G mu. And I haven't proved it, it's not too difficult, one could prove it. And I do know that this is actually a lambda invariant space. But he told me that maybe if he has time, then he will prove in his lecture that if you have an amenable action on a space which is invariant, then it follows that the group has to be amenable. That's it. So that's not too difficult. Let us go back to the example. So if we have now mu, which is lambda absorbing and generating on gamma, gamma, and we want to have a drift. So if I project this mesh down to the z coordinate, I want to have that my lamplighter is more likely to go to the right-hand side. Then I know that the Poisson boundary of gamma and mu is actually, one can show that this is the same as the Poisson boundary of G and rho mu. So, and this is actually the same as just G mod P and mu, where this P is just defined to be, so we have seen before that the Poisson boundary is just this space with the heating measure. So I want to mod out this one. So what do I need to do with what is my P what do I need to do to get here only this, the configuration space? What is P? So if I just take here 0 all over, and here the integers, then I will just only see this, and this is modded out. Okay. And we have seen before that this is the Poisson boundary. And what is nice now on this Poisson boundary is this is what is called prime, meaning that there are no non-trivial factors. So there are no non-trivial boundaries. There is only the Poisson boundary itself and the one-point space. And why is this? Because whenever I would have a factor here, it would be of the form Q, G mod some Q, and this Q would need to contain my P, but my P is a so-called maximal closed subgroup. because whenever I allow here one entry of this configuration to be non-zero, since I have here all of the integers, I can shift and move around this entry and generate any configuration I want to have. So as soon as I have here one entry which is not only just zero, I will get everything. So it's a maximal closed subgroup. One can show that this is absolutely continuous with respect to the Hanna measure on this, and the quotients really look like this. So there cannot be something like this. So there are only trivial subgroups, trivial boundaries. Okay, maybe that's maybe that's a good thing to make a break. Let's now make a break. I don't know, until 1 minute before 1:45. Okay, so now I actually want to talk about a new topic, namely entropy. But before doing so, let me add one last thing to basically this flavor of before this primeness, which actually is maybe also a good connection to the next topic. So I need a date. It was 2003. So if you wonder, okay, what kind of prime boundaries or primes has been studied before, there is a result of Amos-Levaux in 2003, which you probably would not interpret it. We will see now in this case a different version of how to do it, but you can write it as that if you have that your group gamma has Katstan property T, I don't want to define it, but it's like kind of the opposite of amenability. So if you have a group which has property T and it's amenable, and if it's discrete, then it's just finite. Okay, so it's a very kind of opposite way. But if this has property T, then you always know that, and if you have mu being symmetric, finitely supported, and generating, of course, then there exists some mu boundary which is prime. So meaning that there are no further factors down from this mu boundary. This is maybe not the way we will also now say it now, namely now we will actually see property T implies that there is some entropy gap, but you can read it in terms of primeness like this. Okay, entropy. So this is the third thing. More precisely, I'm going to talk about Fürstenberg entropy. So the setup is the following. If we have G acting on X and nu, and just for the definition, I only need actually non-singular. So quasi-invariant. But I mean, think about stationary ones if you want to, that is fine. Then we can define the Fürstenberg entropy of X and nu. This is the integral of minus the log of the rather negative derivative of G inverse nu to d nu of x, and I'm integrating over all x's, and I'm integrating over all g's. This is the so-called Poisson entropy. So why do I need non-singularity? Yeah, exactly. For the negative derivatives here to exist. And so, and it's a nice way of, I mean, usually maybe you're more familiar with entropy when you have an invariant probability measure. But this kind of entropy tells you how far is your dynamics away from being invariant. Namely, just let's understand what it does. So important properties is that, first of all, I mean, the entropy of mu of x and nu is positive. This is just follows by Jensen's inequality. I don't know, we can, maybe if there's time we can do it, but basically you can just minus log is a convex function, you can put it outside of one of the integrals, and then you are left over with something which is just 1, and you have log of 1, and this log of 1 is 0. So this is how you get this inequality. And you do have that the entropy of x and nu is 0 if and only if your nu is actually G invariant. Okay, so you can think of it as some kind of way of measuring how far is this space away from being invariant. Of the negative derivative, sure. I think I don't need that, so let's so the negative derivative, so there is a kind of, okay, so you can write mu of some element A. You can always write it as, so if you want to basically, or should I write just F? Okay, there is a kind of not accurate way of viewing the negative derivative of d nu, is namely that somehow you want to, if you would be allowed to, if you integrate here, and you would be allowed to cancel this out, then what you should get is you should get the integral of what is written here. This is the non-accurate way of looking at it. So what does it mean? It means that nu of G inverse of some element A, you can always express it as the integral of actually an indicator function of A of d G inverse nu d nu with respect on some x of d of nu of x. So this is a way of basically how to go from this probability measure to this probability measure. Okay? It's called a Radon-Nikodym derivative. Okay? It's nice. It as so this exists, since we assumed that G nu is absolutely continuous with respect to nu. Let me write it maybe differently. I mean, it's also true, but let me write it like, yeah, or let me write it like with G inverse, then it's maybe clear. So this is a theorem which says whenever you have nu is absolutely continuous, with respect to this measure, then the radical derivative exists. So then there exists this d g inverse nu d nu. Again, kind of the way you can make kind of students remember it is that, well, you're not allowed to divide by 0. So if you get downstairs 0, you will have a problem. But what I say here is that, well, if you get downstairs 0, then also upstairs you get 0, so you're fine again. That's somehow the kind of the way how to remember it for students, if you want to. Okay? So it's a theorem by Nicodim to say that this always exists and it has this nice property of going from one measure to the other. So there is no need, you can do this in more generality. There is no need to do this for this specific one. You can just do it for some probability measure eta, and this eta should be absolutely continuous with respect to this. Okay, then you would have here eta of A. Okay, this is a way of going from one measure to the other. Yes, true. Yes, yes. It's a function. That's why I write this x value here. It's a nice measurable function. Otherwise, I won't be allowed to write it in this way. Yeah, it's a nice function which allows you to make this transformation. Okay. Does it answer your question? Yeah. Cool. Okay. Okay. Another interesting property is that, but first I need to define, I guess. Okay, let me, yeah, okay, maybe this fits well here. So if we know that, X has no G invariant probability measures, then one can show that the infimum over all, should I write it like, yeah, over all nu which are stationary of the entropy of mu of X and nu is strictly positive. This is something one can show. Also, the entropy behaves nicely with respect to convolution powers, in a sense like if I take the nth convolution power of some x nu, this is the same as n times the entropy of x and nu. And it decays with factors, namely, if we have that we have x and nu, and it has a g factor, y and eta. So we saw last time g factor just means we have some nice measurable map up to some null sets, and the measure here is really pushed down to the measure downstairs is nothing else than the pullback of the measure upstairs, and the group action is nicely equivariant. Then we have that the Fürstenberg entropy of x and nu is always larger than the Fürstenberg entropy of y and eta. So in particular, what we see here, maybe let me fit it here. So in particular, what do we always have? We have the Poisson and the Fürstenberg entropy of the Poisson boundary is always greater or equal than the Fürstenberg entropy of some x and nu for x and nu being the mu boundary. Okay. And so kind of that the Fürstenberg boundary of the Poisson boundary is the maximal is the maximal value. Also, namely, do I write it now or later? Wait. Yeah, there's one more thing I want to say. With actually here. Okay, so we do have the factors. This goes, sorry. It decays with factors. And we have that the entropy of x and nu is equal to the entropy of y and eta, if and only if the map, let's call it pi, if pi is relatively measure preserving. I'll say in a moment what it means. So relatively measure preserving. Where should I? Okay. But I think I do have. Yeah. So are you familiar with disintegration of probability measures? So let's also maybe say what I mean here. So I do have that. So I have this. Let me just copy it. I have pi here and y and eta downstairs. Let me draw this diagram, which your ear always appreciates. So you can think of it as basically above each y, you have some kind of here pi inverse of y, so some kind of fiber. And there is a nice way, namely you can write nu as, let's say, there exists a unique family of probability measures, which we call nu little y, for little y in big Y, such that the following holds, namely nu is nothing else than basically the integral. Now let me write it. Nu of some a is the integral of nu and little y of a intersected with where it lives. So of the singleton here of d eta of y over all y. And this map y is mapped to nu y is measurable. So these two properties here. So there is a unique family which fulfills these two properties, and this is called disintegration of probability measures or of measures. You already know what all these things, namely in the case where you don't have a single element, but you have something which is not a null set, it's just conditional probabilities. Okay? So think of this as a way of having conditional probabilities, but now you actually conditional null sets, which is a bit scary. Okay? But there is a nice way of doing it. It goes back to Rochlin, and it's a very old, nice way. Maybe in some measure theory courses you learn it. And so now I can tell you what I mean with pi is relatively measure preserving. Namely, if this integration family behaves very nicely with respect to the group action, mean that if we have that nu of g y is the same as g of nu y. So what do I have here? I have here y, I have maybe here, I shouldn't wait to, I have maybe here, I'm acting with some G elements, so I have here maybe GY. So above here, I have the same, I have another fiber here. So this was this fiber. And here I have here the fiber pi inverse of GY. And now above here, I would have a probability measure. And I wonder, is it the same probability measure than if I take this measure and just apply the G map upstairs? Okay. So, and if this happens, if this is true for every G, then I call it relatively measure preserving. Okay. And so we do have that if I have a factor map, then I will have equality here if and only if it is relatively measure preserving. Can I do something? Yeah, let me say one more. Okay, it takes. Okay, let me start with something and then next time continue it. So you might have also heard about, or you maybe are more familiar with the random walk entropy. And so now your question should be, okay, how are these things related? So for the random walk entropy, I want to have, again, stick to discrete groups. So let G be discrete. What was my notation? Oh, ugly. Okay, so H random walk. Maybe I will, yeah, okay. Okay, so this is, well, it's the limit, but it's also the infimum just by Fichet, over n of 1 divided minus 1 divided by n, and the sum over all gamma in G, I wrote G in G, the n convolution of this G element times the log of mu of the nth convolution of this G element. So this is the so-called random walk entropy. So any ideas of how they should be related or how you want them to be related? So I mean, instead of the infimum, you can also take your limit, but since it's sub-additive, everything is fine. So should I? Yeah, okay, I will just say one thing or one fact, and then the rest later. Is that the Fürstenberg entropy of the Poisson boundary of G and mu is the same as the random walk entropy. And then next time, or maybe I still have until 10 after. Or I have 2 more minutes. Okay. Okay, then let me continue. Namely, if we have that the entropy is a way of finding out whether something is the Poisson boundary or not. So if you have a candidate for the Poisson boundary, so you only know it's a mu boundary. And you want to say, actually, I do really believe this is the maximal mu boundary I get. This really should be the Poisson boundary. So if this is a mu boundary and you do have that the entropy of this space equals the random walk entropy, then actually you can conclude that indeed, your candidate gives you the Poisson boundary of G and M. So this was done by, maybe I should write Kajmanović-Vršek also. Also this one was also done by Kajmanović-Vršek. Okay, and one more thing. If we have that the random walk entropy is 0, then we do know that the Poisson boundary is trivial. This is not so difficult because we always have that whenever I have, maybe let's take this as another property, whenever I have G acting on X and nu being mu stationary, then you have that the entropy of X and nu will always be less or equal than the random walk entropy. Okay, so all the Fürstenberg's entropies for stationary spaces are somehow bounded by the random walk entropy. Okay, and I think now I will stop. Thank you. So the thing is that I will actually go into exactly computing this entropy in some cases. There are sometimes nice tricks to compute it. So for instance, there is a beautiful trick by Louis Bowen where he uses IRSs in order to show that for the free group, you can obtain all entropy values. So you can really get all, the boundary spectrum is huge. Every entropy value can be realized. But he doesn't really look at the entropy of the boundary, but more he constructs some nice spaces, also called Bowen spaces, and he uses an IRS for this. And IRS means it's an invariant measure, which means it's not seen in the entropy. So it's kind of a way around to look at some bigger space there. Things are nice. There you can have a nice bundle. You can construct things. You can compute things, and then you get full entropy realization in this case. But we will also on Thursday, in my third lecture, I will a little bit. I mean, I won't go too much into details, but somehow say a bit how this primeness, which we have seen today, can somehow be beneficial to give some certain entropy spectra. So sometimes we can have full entropy realization, sometimes we can have very discrete things. But yeah, it's not always so easy to compute. So I think actually to show that something is the Poisson boundary, it's more often used to this Kajmanović strip criteria. But to some extent, it is also based on entropy, his criteria. But people, when they compute something, want to say it's actually for somebody, then they do it with the stripped criteria sometimes. Mm-hmm. Mm-hmm. Yes, exactly. So, I mean, you can also, there is no harm to take really the limit here. And where do I have it here? Maybe Fichte's lemma tells you, well, we do have a sub-additive sequence. So there exists a limit, and this limit actually equals the infimum. That's why I wrote infimum, but feel free to write limit. This is the same. Does it answer your question? it s- I think you're right. Yes. Yes, yes, yes. True. Yes, so definitely entropy is quite useful to for certain things, and yeah, yeah, yes, exactly. Uh, so it is always bounded by the Poisson boundary of this thing. So you can never go beyond the Poisson boundary of this thing. And I mean, in many nice cases, it is bounded, but doesn't have to be now. Yeah. Um, mm, I don't know of any characteristics. I mean, I think in most of the cases, in the web of the examples people start with, this is something finite. This is something actually not too difficult even to compute. Mm, I don't know of an example with infinite entropy.